Hello everyone, this is Kenji Fuji from Chiba Institute of Technology speaking. This time I would like to make a presentation entitled Strength Balance of Steel Damper Columns and Surrounding Beam in Reinforced Concrete Frames. This paper is based on the graduation thesis of the second author, Mr. Mizuki Kato. So let us start from introduction. The topic I would like to talk about is the seismic behavior of reinforced concrete frame with steel damper columns. What I called damper column is shown in the left, while the RC frame with steel damper column is shown in the right. The shear panel damper installed in the middle of column is made of low yield strength steel. This panel absorbs seismic energy as cumulative strain energy. In this study, this steel damper column is installed in the middle span of RC beams. The main purpose of dampers is to minimize the damage of RC beams and columns. The damper panel shown here begins to absorb hysteresis energy when it yields. So the effectiveness of dampers depends on the strength balance of damper columns and surrounding RC members. Following the weak beam strong column concept, the beam ends shown here are considered as the potential hinges. However, the yielding of the beam end sections connected to the damper columns should be avoided because it may lose the effectiveness of damper columns. On the basis of these discussions above, two questions arise. The first question is, what kind of index is appropriate to evaluate it quantitatively the strength balance of steel damper columns and surrounding RC beams? And the second is, what criterion, based on the strength balance, holds for steel damper columns to be effective? So, in this study, we will define the damper column strength ratio based on the rigid perfectly plastic mechanical model. Next, a nonlinear dynamic analysis of frame model is conducted to investigate the influence of damper column strength ratio on the nonlinear seismic response of RC frames with steel damper columns. So, I would like to explain the definition of damper column strength ratio. Let me consider a RC frame with a damper column shown here. For the simplicity in discussions, the following assumptions are made. All RC beams undergo rigid perfectly plastic behavior, and all RC columns are infinitely rigid and strong. This is consistent to the weak beam strong column concept. Let me move to the damper column. All shear panels undergo rigid perfectly plastic behavior, and all elastic columns are infinitely rigid and strong. In the calculation of the internal virtual work, the work done by each plastic hinge at a node is assumed to be the product of the moment at a node and the plastic rotation. We consider two collapse mechanisms shown here. Pi is the assumed horizontal force at each level, while theta p is the plastic rotation. Since all RC columns are assumed to be infinitely rigid and strong, both mechanisms belong to the whole collapse class. For mechanism 1, all shear damper panel is. However, for mechanism 2, no damper panel is. We would like to analyze the collapse mechanism 1 first. Let large lambda 1 denote the collapse load factor for mechanism 1. The external virtual work is calculated as shown here. it is assumed that the internal virtual work of mechanism 1 is the sum of the internal virtual work done by the damper panel and that done by the other RC beam section. The internal virtual work done by the damper panel is calculated as shown here. In this equation, this is the upper bound yielding shear force of damper panel. Next, we would like to analyze the collapse mechanism 2. Similar to mechanism 1, the external virtual work is calculated as shown here. In addition, the internal virtual work of mechanism 2 is the sum of the internal virtual work done by the beam end section connected to damper column and that done by the other RC beam section. The internal virtual work done by the beam end section connected to damper column is calculated as shown here. In this equation, this is the moment at node when the column face moment reaches its ultimate strength. Based on the analysis of two collapse mechanisms, we define the damper column strength ratio as this equation. This damper column strength ratio controls the collapse mechanism. If the ratio alpha is smaller than unity, collapse mechanism 1 occurs, while in case that the ratio alpha is larger than unity, collapse mechanism 2 occurs. Next, I would like to explain the frame model and ground motion data. Here shows the simplified frame model used in this study. This is a simplified 4-story frame model based on 10-story frame model. In this study, the lower 4 stories are considered. The floor mass of level 1 to 3 are assumed equal, while the floor mass of level 4 is assumed considering the mass of upper floors. Here shows the envelope of force deformation relationship of the nonlinear flexural spring of RC members. For the beam ends, the envelope is modeled as trilinear curve considering stiffness degradation due to crack and yielding of the sections. While for the column ends, the envelope is modeled as bilinear curve considering only the stiffness degradation due to crack of the sections. Here shows the hysteresis rule for nonlinear dynamic analysis. In RC members, shear failure is not considered and the behavior of all members are assumed in ductile manner. Modified Muto model shown in A is used for the nonlinear flexural spring at each RC member end. And in damper columns, the hysteresis model proposed by Ono and Kaneko shown in B is used for the nonlinear shear spring. This model can consider the strain hardening effect. Note that the flexural behavior of damper column is assumed to be elastic behavior. In this analysis, the structural parameters is the strength balance of the damper column and surrounding RC beams. The assumptions regarding yield strength of the beam sections connected to damper columns are explained. Here shows the bending moment at the beam end section connected to the damper columns. In this figure, the shear force of damper columns are assumed to be the upper bound of the yield strength of damper panel. So we can calculate the moment at node C. Then assume that the beam end A1 and B2 yields. From this figure, determine the yield strength of beam end sections B1 and A2 correspond alpha equals unity. Given the above, the yield strength My at beam end sections connected to damper columns are determined using beam end strength ratio alpha z. In the study, alpha z is set from 0.7 to 1.5 with step intervals of 0.1. The moment deformation relationship is assumed as shown here. The cracking moment MC and the second tangent stiffness degradation ratio at yielding alpha y is set independent of alpha z for simplicity. This figure shows the relation between the beam end strength ratio alpha z and the damper column strength ratio alpha. When alpha z is smaller than unity, the damper column strength ratio is larger than unity. In such case, the mechanism too would occur. When alpha z is larger than unity, the damper column strength ratio is smaller than unity. In such case, the mechanism 1 would occur. Here shows the elastic response spectra of artificial ground motions used in this study. The pseudo acceleration spectrum is shown in the left, while the total input energy spectrum is shown in the right. In this study, 10 artificial ground motions are used for nonlinear dynamic analysis. The target spectrum for the generation of artificial ground motions is determined from the building standard law of Japan. In this study, the scaling factor of 10 artificial ground motions are set 0.5 and 1.0. So let us move to the analysis results. In this study, average of results obtained from nonlinear time history analysis of 10 artificial ground motions were considered. This figure shows the relationship between the maximum of the whole deformation angle R star max and the damper column strength ratio alpha. The result, when scaling factor equals 0.5, is shown in the left, while the result, when the scaling factor equals 1.0, is shown in the right. Note the maximum whole deformation angle is determined as the peak horizontal displacement at level Z4 divided by the total height H4. As is shown here, the whole deformation angle increases as alpha increases. The maximum whole deformation angle is around 0.01 radian when the scaling factor is 0.5, while it is around 0.02 radian when the scaling factor is 1.0. Here shows the relationship between the total input energy, the cumulative strain energy, and the damper column strength ratio alpha. The input energy and the total strain energy are stable when alpha increases. However, the cumulative strain energy by RC frame increases as alpha increases. In addition, the cumulative strain energy by damper column decreases as alpha increases. The border value where the cumulative strain energy of RC frame exceeds that of damper column is around 1.1 when the scaling factor equals 0.5, while in case that the scaling factor equals 1.0, the border value is around 0.9. Therefore, the effectiveness of the damper column is lower as alpha increases. Based on our numerical results, in case that the expected whole deformation angle is close to 0.02 radian, the strength ratio alpha should not exceed 0.9. Next, our discussions begins from the plastic rotation of the beam end connected to damper columns. Here shows the beam end connected to damper column. This figure depicts the definition of the plastic rotation angle. Here, theta p max is the peak plastic rotation angle. When theta max is smaller than theta y, theta p max is 0. In such case, no yielding occurs. This corresponds to mechanism 1. While when theta max exceeds theta y, yielding occurs. This corresponds to mechanism 2. Here shows the relationship between the peak plastic rotation at beam end connected to damper column at each level and the damper column strength ratio alpha. As expected, theta p max increases as alpha increases. For the scaling factor equals 1.0, theta p max is close to 0 when alpha is less than 0.9. Therefore, the behavior of the simplified frame model is similar to mechanism 1 when alpha is less than 0.9. Next, focusing on the behavior of the damper panel, here shows the relationship between the peak shear strain of the damper panel in each damper column gamma d max and the damper column strength ratio alpha. As expected, gamma d max is large and stable when alpha is small. In addition, gamma d max decreases rapidly as alpha increases. Note that in the case of scaling factor equals 1.0, the peak shear strain gamma d max reaches 5% when alpha is less than 0.9. In such case, the damper panel is close to ultimate stage. Therefore, the case alpha equals 0.9 seems suitable in eliciting full performance from damper columns. Finally, I would like to move conclusions. In this presentation, the strength balance of steel damper columns and surrounding beams in RC frame with damper column is investigated. First, damper column strength ratio is defined as this equation. The proposed damper column strength ratio alpha is the potential index to discuss the strength balance of steel damper columns and surrounding beams. Based on the numerical analysis results shown here, the ratio alpha should be less than 0.9 when expected hole deformation angle is close to 0.02 radian. This is the end of my presentation. Thank you very much.